Now that my twin traveler younger sibling has deduced the transformation equations for velocities, we have a broader picture of the transformations in special relativity. Let's play a bit with this. Let's consider there is a spaceship that is leaving the Earth, initially addressed to the stars. In order to be propelled, the ship will experience three impulse phases. In each one of these phases, the engines will kick the ship. This will accelerate and the ship will gain velocity. The kicking phases are such that each impulse makes the ship gain the same amount of speed with respect to its rest inertial frame. So, initially, it gains a velocity v with respect to Earth, the inertial frame 0. Then it stays for a while in the inertial frame 1 with a relative velocity of v with respect to Earth. Then activates phase 2. This phase gives the ship a velocity v with respect to inertial frame 1. Then it stays for a while in inertial frame 2, and then another kick gives the ship a velocity v with respect to inertial frame 2. Now, what is the final velocity, the final speed that the ship will have with respect to Earth, to inertial frame 0? To know that, we need to apply the addition of velocities several times. Well, this is the equation of transformation of velocities on the x-axis, and that's the spaceship is moving in a straight line, so we can always choose that to be our x and x prime, x prime, x3 prime axis. So because it's going to be an x-axis, I'm going to just remove that x, so I will write this expression as... And now I will write indexes 1, 2, and 3 to refer to the different reference frames. So, for example, the velocity of the spacecraft when it is in the 1 reference frame, that velocity u sub 1 is going to be v. Just the first boost just gives a velocity v with respect to the Earth. Now, when there is the second boost, now we have two reference frame. The first one is Earth address. Now the other reference frame is this reference frame, which is where the spacecraft is after the first boost. Now, because it's going to be kicked with a second boost, we'll leave this reference frame and jump into this other reference frame. Now is when we need to apply this expression here. So now we're looking for the velocity u sub 2 that will have the spacecraft when it's in reference frame S2, which is the velocity prime of the spacecraft in reference to, the prime is making reference to the previous reference frame S1. So this u prime 2 is the speed that has the spacecraft as seen from, when it is in 2, as seen from 1. So this plus v divided by 1 plus u prime 2 v over c squared. Now, because u prime 2 is the velocity of the spacecraft when it is in 2 as seen from 1, we know that that velocity is going to be v. So now this u prime 2, if we apply that here, then we have v plus v, which we rewrite as... So that is the velocity of a spacecraft when it is in 2 as seen from the Earth. After the third boost of velocity that moves the spacecraft from reference frame 2 onto reference frame 3, remember that the velocity that the spaceship has at 3 as seen by 2, which we call this u prime 3, is v. That's happens for all of them. But now I have to rewrite this equation here. But now I want to find the velocity 3 of the spacecraft when it is as seen from Earth, which will be the velocity of prime as seen from this reference frame plus the relative velocity of these two reference frames. So now I'm going from S0, S2, and now the spacecraft is here, which is S3. Now the v that I have to use now, I will call it v2, which is the velocity of reference frame 2 with respect to Earth, which is this one. So this is what I will have to substitute right on this v here. Let me write it down here. Now this v2 is all this term here, the velocity of reference frame 2 with respect to the Earth.
u prime 3. Now here we know that u prime 3 is equals to v, which as a matter of fact was written up there. So let me substitute things here. V plus v2 over 1 plus vv2 over c squared. And now instead of v2 I will write that. So blah blah blah, that's going to be v plus all this stuff here. That simple equation. Now let's simplify this a little bit. Here I can multiply by 1 plus v squared. Here this is going to be v parentheses. And down here I have v over c, that is beta. So this is, and then I will multiply this 1 plus v squared there. And that can now be simplified, cancel this 1 plus v squared with this 1 plus v squared. I will write it down here. And now this is getting simplified, so this is 3 plus beta squared, and this is 3 beta squared plus 1. So that is the velocity that the spacecraft will have when it is in this reference frame 3 after the third boost as seen from the Earth.
Well, this final velocity is the one we would observe from Earth. Looked at from a classical point of view, if the relative velocity v is small, beta is negligible, and this simplifies to 3 over 1, which is 3 times v, as expected. But if the velocity is almost that of light, if beta is almost 1, we have 3 plus 1 over 3 plus 1, which is 1, and the velocity, as observed from Earth, is almost c, but not greater than c. We can boost the ship again and again and again, but we'll never cross the limit of the speed of light. So, stay safe, don't drive faster than c, and may the science be with you.